Hey everyone, today we are jumping into some absolutely wild research. Seriously, this could completely change how AI learns, taking it out of these giant data centers and putting it right into the tiny gadgets we use every day.
Okay, so think about this for a second. You get a brand new smartwatch, and you've got this unique workout you do. Why can't you just teach it to the watch and have it learn right there on your wrist? Well, the truth is, most AI just doesn't work that way. The real learning, the heavy lifting, happens miles away in the cloud. And this really breaks down the two worlds we're talking about. You've got your data center AI, which needs that constant internet connection and a ton of power to slowly learn new things offline. And then you have the dream of edge AI, devices that can learn right now, on their own, without guzzling power. For a long time, this has felt like science fiction, but that might be changing. So, before we get to the amazing solution, we've got to understand the problem. And there are really three big roadblocks, well, let's call them villains, that have been holding back smart devices. First up, the math itself. Traditional AI relies on what's called floating point math, and it's just way too complex and power hungry for a tiny chip running on a small battery. Second, the way AI learns, this process called backpropagation is just massive. It's like trying to run a supercomputer on a watch battery. It's not going to happen. And third, and this one's kind of wild, is this thing called catastrophic forgetting. You teach an AI something new, and poof, it just overwrites and forgets the old stuff. Not very smart, right?
So how in the world do you get around all these huge problems? Well, the researchers behind this paper did something completely different, something that's actually inspired by how our own brains seem to work. It's called hyperdimensional computing, or HDC. Now, stick with me here because the core idea is actually brilliant. Instead of doing all this complicated math, you take your data and you blow it up into a huge high-dimensional space. You turn it into a massive, unique pattern, like this 8,192-bit vector here. Once you've done that, learning becomes way, way simpler. It's not about calculus anymore. It's just about comparing these giant patterns to see which ones are similar. And this quote from the paper just nails it. You're not doing this intense, heavy computation to figure things out. Nope, you're just doing a geometric search. The AI is basically just asking, hey, does this new pattern look like any of the other patterns I've already seen? It's a much easier question to answer. Okay, to really get this, let's use an analogy that makes perfect sense. Forget about numbers for a minute. Instead, I want you to think about really, really long, unique barcodes. Every single piece of information from a sensor, a movement, a temperature reading, whatever, it's no longer a number. Instead, it gets transformed into one of these unique binary fingerprints. We're talking about a string of ones and zeros that's thousands of characters long, representing just one specific moment. This makes everything super distinct and really easy to compare. And the way they create these barcodes is incredibly slick. The system grabs the sensor data, gives each piece a unique ID, and then uses a lightning-fast operation called XOR to combine them. XOR is just a super simple, efficient way for computers to merge binary patterns. Then, all these little barcodes are bundled together into one final massive vector that represents the whole picture. And here's the absolute game changer. This entire process, this whole pipeline, completely throws out the heavy machinery of old-school AI. No more of that power-draining matrix math. And no more backpropagation. It's a system designed from the ground up to be lean, mean, and incredibly fast. All right, so we've swapped out the old, clunky engine for this new, brain-inspired one. So how fast is it really? Honestly, the results are just nuts. 0.96 milliseconds. I mean, let that sink in. That is less than 1,000th of a second. And get this, that's how long it took the system to learn a brand new activity it had never seen before, from just 5 examples. And remember that whole catastrophic forgetting villain we talked about? Yeah, gone. It learned the new thing perfectly, and it didn't mess up any of its old knowledge. This table shows you just how well it worked. Look at the precision for the new class, a perfect 1.0. What does that mean? It means every single time the AI said, hey, I think that's the new activity, it was right. Every single time. 0 false alarms. Now, the recall is a bit lower, which just means it sometimes missed seeing it, but that's what you'd expect when it only learned from 5 examples. The bottom line is it learned a flawless new category in under a millisecond. That's insane. Look, this isn't just some cool lab experiment. This kind of crazy performance unlocks a future where real intelligence is actually embedded in everything around us. Just think about it. You could have IoT sensors that learn and adapt to their environment, medical devices that learn your body's personal patterns to give you better care. You could even have handheld devices that analyze DNA sequences out in the field, in real time. This is the kind of stuff this research opens up. And this slide gets right down to the nitty-gritty of why this all works so well on tiny chips. Old-school AI needs power-hungry processors. This new way, though, it can run on simple, low-power things called lookup tables, which are basically just super-fast cheat sheets for a computer. It trades complex math for simple memory lookups. And because it's so direct, the speed is always the same, always predictable, which is absolutely perfect for real-time applications where every microsecond is critical. So the big takeaway here is that we might be on the edge of a massive shift. A shift from devices that are just programmed to do a task to devices that can genuinely learn and adapt all on their own in an instant. And that leaves us with a pretty exciting question to chew on. What will we create when every device can learn on its own?